Hey, this is a video for a calculus student getting ready for his upcoming midterm with antiderivatives. Here, the teacher presented 5 review problems. Each one of these is a skill for derivatives and antiderivatives. The first function is a polynomial with positive exponents. The second function has negative and positive exponents. The third example had fractional exponents. The fourth antiderivative was the natural log. And the fifth derivative was using your algebraic skills to rewrite the function so that the derivative can be done as 2 separate integrals. So before we see the solutions for these, I plotted each one on Desmos using the function tool, as you can see here in the screenshot. And all 5 graphs are presented together in a local 30 by 20 picture here. Here's function number 1, which you can see is mostly in quadrant 3 and in quadrant 1. But when it crosses over at the origin, that squiggly line shows that there's some local activity going on between the values of -1 and 1, certainly for this function. The second example is related to the parabola 4x squared. But that first term is what creates this dimple here, because as x is less than 1, you're going to get terms that become increasingly large. For example, if x is a 10th, then a 10th squared is 100th. So it's 5 divided by 100th, which is 500. So as x gets closer and closer to 0 from the left or right side, the limit is infinity. So instead of it being a parabola, it's got this sort of W shape. But remember that the center line is an asymptote, and the function only really exists in quadrant 1 and quadrant 2 separately, but does not exist at x equals 0. It goes up to infinity. Question number 3 was x to the 1/3. And if you think of the inverse function y equals x cubed, you know that the inflection point is at 0, but here instead of it being horizontal and flat, it's vertical, because this is the cube root function, not the cube function. Example number 4 from the teacher was the hyperbola 1/2x, which is related to the basic function 1/x. It's just scaled a little bit differently, so that corner roundedness will be a little bit sharper shape, I think, or less sharp, depending on the constant. The last one was another hyperbola, like number 4, but the center of it, that invisible point that's not, like the center that's not part of the curve itself, here you can see that it lifted up by 1 unit. So the center of this hyperbola is at 0, 1. In example 4, the center of the hyperbola, even though it's not a point on the function, is at 0, 0. So now we'll look at the solutions for each one for this student's review. And I hope these slides are useful to you as you prepare for your midterm exam. For question number 1, what we do is when we have a polynomial, we would write it as the integral of 3x to the 5th minus 5x to the 9th. By the power rule, each exponent will go up by 1 power level. So we know that the first term will become x to the 6th, and the second term will become x to the 10th, plus a constant, because we don't know where the midline of the function is. It doesn't matter if it's x to the, once we solve it, if the constant is 0 or 100 or -100, it doesn't matter. So we just write that as c. That doesn't change the shape of the curve or the rate of change of the curve. What we do to set the correct coefficients in front is we just take 1x to the 6th and 1x to the 10th, and we can do the derivative to make sure that we don't make an error. Well, the derivative of x to the 6th by the power rule is 6x to the 5th. But we didn't have 6x to the 5th. We had 3x to the 5th. So the coefficient that's a part of this, of the integral, is 1/2. Similarly, for the second term, the derivative of x to the 10th is 10x to the 9th, but 5x to the 9th is present, so we need to scale that also by 1/2. Now that we've scaled each function, each term by its coefficient, by these coefficients to match the function above, we get the correct answer, a half x to the sixth minus a half x to the 10th plus c. For question number 2, we have 5 over x squared plus 4x squared. So what I did here was I rewrote the first term with x as a negative exponent. Then the power rule still applies because you just add 1 unit to the negative value there. So that means that by integration, the first term, 5x to the second, will become some number times x to the negative 1. And 4x squared, well, the x squared will become x cubed. To find the correct coefficients, we'll take the derivative by the power rule. X to the negative 1 would become negative 1x to the negative 2, and x cubed is 3x squared. Well, we didn't have negative 1 in front of that x squared. We had 5. So we have to scale it up by negative 5 to make the coefficient match. Similarly, we need to take 3 and multiply it by 4/3 because that's 12/3, which is 4. So now we've scaled each coefficient term by term to match the function above, and the correct answer is negative 5x to the negative 1 plus 4/3 x cubed plus c for question 2. Question number 3 was the integral of 6 times, I think it read the cube root of r, but I just rewrote these all as I have coded it in Desmos with variable x, with free variable x. So then again, the power rule with integration applies. It's 1/3, you add 1 to it, that becomes 1/3 plus 1, or 1/3 plus 3/3 is 4/3. So then taking the derivative of 4/3, we would have 4/3 x to the 1/3. But there was a 6 as the coefficient, so we have to solve that problem. So I put it in a blue box on the right here. 6 is the coefficient, and that equals some amount times 4/3. Multiply both sides by 3/4, and 6 times 3 is 18 as the numerator, divided by 4, and reducing that by 2, we get 9/2. So that's the scale we need for this term so that the coefficient matches the original function of the given integral, of the given indefinite integral. So our answer is 9/2 x to the 4/3 plus c. For question number 4, the teacher gave us the derivative of 1 over 2x. Well, what we do for these types of equations is we factor out any constants that we can from the numerator and the denominator to the left, because we can do that with integration. So the 2 is in the denominator, so we factor out 1/2 and write it as a half of the integral of 1 over x dx. This is a pattern, because x to the negative 1, if we add 1 to it, would be x to the 0. Well, that's a dead end because x to the 0 is the constant 1. So we know that that's incorrect. In your calculus textbook is the official proof showing that the integral of the harmonic series 1 over x is the natural log of x plus c. So you needed to know that this is the special case of that exponent which would make a 0. This is the only case if we have x to the negative 1. So that is not undefined. It becomes the natural log of x plus c. Then taking the derivative, we can see that we would have, oh, I wrote this down wrong. Let me fix that. We would have 1 over x plus c is what should be written there. Forgive me, I need to fix that. The derivative of ln of x, of course, would bring us to 1 over x. All right, but we didn't have 1 over x, we had 1 over 2x. All we have to do is bring that constant that we left factored down, and we have the correct scaling. So that would bring us back to the original. That would match the coefficient of the original function. And the answer is a half times the natural log of x plus c for question 4. The last question given by this professor to this college student, question number 5, was, can you do the indefinite integral of x plus 1 over x? As you can see, this was a hyperbola as well, but the center of the hyperbola was at the point on the map 0, 1. It was shifted up 1 vertical unit. However, we don't have a technique or a u substitution which really works for the numerator and denominator here with respect with dx. So what we do is we divide by the monomial for both terms above. And we rewrite it as the integral of x over x plus 1 over x dx. The first integral is the integral of 1, and then the second term of the polynomial is 1 over x dx. Well, we know this pattern by now. We know that the integral of any constant is that constant times x. So here it's 1x, but I simply wrote it as x. And we know the pattern of the special case, the integral of 1 over x, is the natural log of x plus c. So the correct answer for question number 5 is x plus ln x plus c is the antiderivative. Again, I hope the student is doing well and enjoying their studies for a non-math major here in undergraduate college in the United States. Thank you for watching my video, and good luck to you on your upcoming midterm exam.